Hello, and welcome to Lecture 3 of Session 13 of the LSSTC Data Science Fellowship Program. We've already seen lectures on Fourier analysis and Gaussian processes as a way to deal with time series data. And today I'm going to talk about one of the fundamental problems for astronomical time series, and that is measuring periodic signals, in particular in time series that have gaps and heteroscedastic uncertainties. So let's jump on in. We're going to focus on essentially data as it comes for ground-based surveys, or what we will ultimately see with the Rubin Observatory today. So we cannot use standard Fourier techniques in order to measure periodicity or other frequencies that may be present in the data. Before we start, I just want to note that this lecture has been strongly influenced by Understanding the Lomb-Scargle Periodogram by Jake van der Plas. And I also highly recommend that you check out the Lomb and Scargle papers that essentially gave rise to the Lomb-Scargle Periodogram. There are many, way too many papers in the literature on Lomb-Scargle and other ways that you might go about detecting periods in astronomical data. There is a pretty good summary led by former DSFP lecturer Matthew Graham and some colleagues, where they took a systematic look at several of the most popular algorithms that are used to search for periodic signals. And in particular, they actually tested these methods on actual astronomical data. So there was no idealized conditions or sort of forced uncertainties where you don't have these weird outliers that we almost always see in astronomical time series. So I highly recommend that paper. Somewhat to my dismay, there is no single right answer. So depending on your particular application, you may have a different algorithm that works best in terms of finding the period. There's going to be a lot of things that we do repeatedly throughout today's lecture. In particular, we're going to generate some periodic signals over different grids of sampling times, as well as making phased plots. So that's essentially taking a full string of time series data and then figuring out where everything fits in phase space if you have a given period for your signal. So with those two things in mind, we're going to first start by jumping in on some helper functions. All right, so while this is a lecture, we're actually going to start with a problem today. I would like for you to write a function called gen periodic data that creates simulated data, including noise, over a grid of user-supplied positions. So we're going to have a function y equals a times sine 2 pi x over p minus phi plus some uncertainty sigma y. Okay? A is an amplitude, p is the period, phi is just some phase offset, and these are all going to be inputs to the function. And as a reminder, we do want some random Gaussian noise included here. For those of you that are watching at home, I highly encourage you to pause the lecture at this moment and continue to work on the problems on your own. Otherwise, I will proceed with the solutions. All right, so we see here that we have gen periodic data, and we have input of x, and then defaults for the period, amplitude, phase, and noise. Okay, all of which can be supplied by the user, but they don't need to be. And now we need to complete this function, right, which we see here at the bottom of this cell. So we know that we want y to be equal to the amplitude, okay, multiplied by the sine of 2 pi. So we're going to do 2 times numpy pi multiplied by the input x, okay, divided by p. All right, that's the period, which we are inputting as period, minus the phase, which is just called phase. Right? Okay, so that's the signal, essentially, y, and then we also want there to be uncertainties on y. So for that, we will say we want a random number generator, and in particular, we want to generate random numbers from the normal distribution. We want the mean on that normal distribution to be 0, And we can see here that the noise is actually input as the variance of the noise, but this particular function wants the standard deviation. So we'll take the square root of the noise term here. And then the last thing to do is to set the size of this uncertainty array. We want it to be the same length as L. So we can say size equals len. I said length is L, I meant length of Y. So size equals the length of Y. So now we'll get random scatter on each of our input positions, and then we're going to return Y plus dy. All right, so let's execute that. No problem so far. Now we'd like to generate a noise-free signal with a equal to 2 and p equal to pi over a regular grid between 0 and 10. Basically, we want to check that our function works. OK, so we want a grid from 0 to 10. And I don't know, let's pick 1, 2, 3. Why not? 123 points. And then for generate periodic data, we need input positions x. We want an amplitude of 2. And we want a period of pi, we said. And then it looks like all of the plotting function has been given to us already, so we can just execute this cell. OK. And here we have our results. And indeed, it looks like we have a sine curve that does, in fact, have a period that is equal to pi. OK, excellent. All right, so now we want to create another helper function called phase plot. And this will take as input x, y, and p, and then create a phase-folded light curve. And if you're not familiar with this term, the basic idea is if we consider one cycle of an event, basically the time that passes between 0 and p, or p and 2p, essentially a full cycle of the data, okay? We want to just phase up all the data so that it exists between 0 and 1, right? Again, consisting of a single phase of the data. We also want this function to have an optional argument, y uncertainties, so that we can include uncertainties on the y values if they are available for our data. OK, so if we want to figure out where the phase is for everything, and that's something it looks like we're going to have to calculate in this particular function that has inputs x, y, and a period on which to fold. Okay. Then what we need to do is we have phases here. There's a few different ways you can do this, but my preferred way to do this is to just take the input time series or x values, divide that by the period. Okay, so essentially this is going to tell us how far along in every new periodic cycle your positions are, and then we can take the mod of that with 1. The other way to do that is you could take the mod of the data with the actual value of the period itself, and then just divide by the period, and that'll also line everything up between 0 and 1. Otherwise, all of the commands here are done for us, so we can execute this cell, right? And then as a final test, we want to plot the phase-folded data that we created in problem 1 sub b. All right, so this is just going to take as input our values x, y, and the period, which is np pi. And there were no uncertainties on this data, so we don't need to pass an argument for that. All right, and here we can see that indeed this does look like a sine curve, right? And we have everything basically lining up between phase 0 and 1. All right, so that's great. Our helper functions are ready to go. Now we can dive into the more meaty content of this lecture. All right, so before we really jump into Lomb-Scargle, I actually want to spend a little bit of time doing a review of Fourier analysis. And if this is entirely new to you, I strongly recommend that you go back and check out lecture number 1 from this series, where a more in-depth introduction to Fourier methods and Fourier analysis is given. Okay. As we covered in the very first lecture from this session, the introductory lecture, when you have an astronomical time series, one of the fundamental things, the things that we care most about measuring, is a periodic signal of some kind. And that's because periodic signals provide absolute insight into the physical nature of the systems that we are studying. So if you have some eclipsing binary, the period will tell you about the masses of those sources. If you have some star that is pulsating, that pulsational time scale can tell you about the inner composition of that star or its physical size. So these period measurements actually directly connect us to physical properties of the systems. And when it comes to measuring periods in astronomical data, the standard choice is the Lomb-Scargle Periodogram. Okay. At the heart of understanding any periodic signals, though, is Fourier analysis. And so to better help us understand how to interpret what we will ultimately measure with the Lomb-Scargle Periodogram, we're first going to consider Fourier transforms. And again, this is covered in more detail in Lecture 1 from this session. All right, so just as a quick overview, reminder, if you have some continuous signal, g of t, the Fourier transform of that signal is defined as the integral from -infinity to infinity of g of t multiplied by this exponential factor, -2 pi I multiplied by f, that's a frequency, times t, dt. And in this case, I is an imaginary number. Okay. Similarly, the inverse of this equation is defined as the integral from -infinity to infinity of the Fourier transform at f, okay, e to the 2 pi I f of t df. And in short, Fourier transforms provide a method to move some signal that's been measured in time space. That's almost always how we measure things, right? We just have some clock that's ticking along, and at various points in time, we measure some sort of signal. That's what our g of t is here. Doing the Fourier transform essentially breaks that signal up into its component frequencies, or the dominant frequencies that are present within the data. Okay. For convenience, for the rest of this lecture, we're going to use the Fourier transform operator, which is this scripty f symbol that I'm showing on the screen here. And using that symbol, the previous equations reduce to the Fourier transform of g is equal to g hat, and the inverse Fourier transform of g hat is equal to g. All right, so it's actually possible to go back and forth from the time domain to the Fourier domain and back. Okay. There are many different useful properties of the Fourier transform, including the fact that it is a linear operator. Furthermore, a shift in the signal in time imparts a shift in phase in the Fourier transform. Okay, so that's also very useful. But most importantly, as we consider things like measuring periodic signals, okay, is the fact that for the Fourier transform, the squared amplitude of the resulting transform allows us to get rid of the imaginary component, and in turn measure the power spectral density, or the power spectrum. This is how, going back to what I said, you understand what are the dominant frequencies that are present in any signal that you may have. Okay? And we're going to write this PSD, or power spectrum, as this scripty p, right? So script p sub g is equal to the squared amplitude of the Fourier transform of g. The power spectrum is a real valued function, and it quantifies the contribution of every frequency f to the total signal in g. So this is a way to basically find whatever your dominant frequencies are. So now we're going to look at some common Fourier pairs. Basically, here's a common or standard continuous function. What is the Fourier transform of that function? And looking at these common Fourier pairs is actually going to prove extremely helpful in terms of how we interpret the Lomb-Scargle Periodogram. Right, so here we have 4 Fourier pairs that I want to discuss in detail. All right, so the first one is one of the most common and simple continuous signals you could imagine, a sinusoid. Right? So here we have a sinusoid, and the Fourier transform of a sinusoid, right, just creates a delta function, where that delta function is located at the frequency, or 1 over the period, which you can see here on the left, of that sinusoid. Okay? So the sample problem we had before with a period of pi, taking the Fourier transform of that continuous signal would give you a delta function at pi and at negative pi. Okay? All right, furthermore, the Fourier transform of a Gaussian is also a Gaussian, just the variance changes as a result of the transform. The Fourier transform of a top hat gives you a sinc function. We'll come back to why this is important in a little bit. And then finally, the Fourier transform of a Dirac comb, right, which is essentially just a series of delta functions all of which are spaced by some common interval. In this case, we'll call that capital T, right? The inverse of that, the Fourier transform of that is also a Dirac cone, except the spacing is now 1 over T, right? So in time space, the spacing is T. In frequency space, the spacing is the frequency, essentially, 1 over the time. Okay. Now, these common Fourier pairs are especially useful in light of the convolution theorem. So Fourier transforms convert convolutions into pointwise products. We can define the convolution in the following way. So f convolved with g is equal to the integral from -infinity to infinity of f of tau multiplied by g of t minus tau d tau. And in this case, this little star is the convolution symbol. The way to visualize this is that essentially you have two functions, and you're just going to slide them past each other, essentially taking like the multiplicative product everywhere as they are slid past each other. Okay? That is what a convolution is. Now, from the convolution theorem, right, the Fourier transform of f convolved with g is equal to the Fourier transform of f multiplied by the Fourier transform of g. Furthermore, the Fourier transform of a product is equal to the convolution of the Fourier transforms. So the Fourier transform of f multiplied by g is equal to the convolution of the Fourier transform of f with the Fourier transform of g. Right. This particular theorem, the convolution theorem, is incredibly important for helping us to understand the Lomb-Scargle periodogram. And I want to return now to our Fourier pairs to try to see why that is. Right? So suppose we have some star out in space and it's rotating. Okay? So it's got some rotational period, and as far as we're concerned, it's just going to keep rotating forever, even though technically that's not true. Let's just assume that's the case. All right, so that's some basically baseline signal of a sinusoid. Okay? Now, we will never be able to observe that rotation for all of time. In fact, we will either have some survey or just our lifetimes, right? Both of which are finite. So that means that ultimately, if we're looking at some star that's rotating, what we're going to do is multiply some top hat function, where the start of the top hat, where we go from 0 to 1, that occurs at, let's say, the start of the survey, the start of the Rubin Observatory, for example. And then that's going to continue all the way till the end of the survey. Okay, so that's 10 years for the Rubin Observatory. So now what our signal is, what we actually observe from this star that we're observing, is this top hat multiplied by the sinusoid. Okay. Well, the Fourier transform of that is then going to be the convolution of a delta function with a sinc function. So that just means we're going to get a couple of sinc functions beating against each other here. Okay. But we also aren't able to observe continuously. Right? We have to make observations, let's say, once every day. Well, that's exactly what's being described here by this Dirac cone. So if we multiply our Dirac cone by our top hat, by our sinusoid, we'll essentially have a bunch of observations that are tracing out, okay, the rotational signal from our star. The Fourier transform of that is then going to be the convolution of a delta function with a sinc function, with another delta function that's related to the frequency at which we are able to observe the signal. Okay? And we're actually going to see all of that structure in just a little bit in our Lomb-Scargle periodogram, essentially our estimate of the power spectrum. Okay. So Fourier transforms are excellent, and they're great, and I'm glad that we have all become experts now in a few days with the DSFP. But ultimately what we care about is a measure of periodicity and the actual observations of our astrophysical sources. And we have no detectors that are continuous, right, where we can just see a signal at all points in time. But we also, due to the finite nature of our lifetimes, have no signals that are infinite. Okay? So the integrals that are necessary to perform a Fourier transform are not going to be particularly helpful to us as we try to measure periodicity in our light curves. Okay? So we can't ultimately use Fourier transforms. Okay. The other thing that I want to point out real quick as an aside is that the very first thing to understand when we talk about real-world observations as opposed to continuous signals is the Nyquist frequency limit. And basically the Nyquist limit is the following. If you have observations that are obtained in a uniformly spaced manner at a rate of f0, so that's the frequency, 1 over t, so t is the gap between every observation that's obtained, right? One can only recover the frequency information if the signal is band limited between frequencies of plus or minus f0 over 2. Okay? To put this another way, the highest frequency that can be detected in any such data is f0 over 2. Okay? I think this is actually easiest to see with an example, so that'll bring us to our next problem today. Now, if you're working at home, again, a reminder, I recommend that you pause and try to work through the problems before we go through the solutions as part of the lecture itself. All right, so now I want to generate and plot a periodic signal with f equal to f Nyquist equal to 1/2 on a grid from 0 to 10, comprising of 10 even samples, i.e. 0, 1, 2, 3. Oh, actually, that's a little mistake, isn't it? This should be 11 even samples because we want points at 0 and 10. OK. And then overplot the underlying signal in addition to the observations themselves. OK, so we want a grid from 0 to 10. And we have a periodic signal with frequency equal to 1/2. All right, so we're going to have a grid from 0 to 10 with 11 points, which is what we just said. And then we want to create a signal over x with a period equal to 2, okay? Or the Nyquist frequency. And then we also want to generate the underlying signal. So that'll be from 0 to 10. And we just need a lot of data points. Let's just say 1, 2, 3, 4. And the signal in this case is going to be generated at x signal, okay, again with a period equal to 2. All right, so all the plotting is ready to go. So we can execute this cell. Okay, and what do we notice here? Well, it turns out that if we sample exactly at the Nyquist frequency, you'll see that all of the observations, the blue points here, are actually equal to y. Oof, that's not good. So we have this periodic signal, but by sampling at the Nyquist frequency, we actually fail to actually capture any of the variability in this particular signal. That's not great. OK, but does that mean that just the Nyquist frequency is special? What if the frequency is greater than the Nyquist frequency? OK, so as above, let's generate and plot a periodic signal with a frequency of 0.7 on an even grid from 0 to 10. All right? And let's overplot the underlying signal in addition to the observations. So this is very similar to what we just did. We're just going to have a different period in this case. So we have a grid from 0 to 10 with 11 points. And then we want to generate data at x with a period. We set a frequency of 0.7. So our period is 1 divided by 0.7. Okay. And our signal is going to be from 0 to 10 with 1, 2, 3, 4 points. And our y signal is going to be generated at x signal and a period equal to 1 divided by 0.7. And I just noticed a quick typo. This should be 0.7. OK, the plotting is there for us, so we can execute this cell now. OK, great. Oh, so now clearly there are variations in the data. That's great. You can see several observations here, OK, at different phases. So we have recovered a variable signal. So if we're not right at the Nyquist frequency, we can detect variability. That's great. OK, so this source is variable. But let's go back. There are fewer than 2 observations per cycle. So let's just confirm that, right? So here's a minimum, 1 observation, right? Here's a maximum, 1 observation. Maximum, all right, maximum to maximum, 1 observation. OK, so per cycle there are fewer than 2 observations. So let's now overplot on what we just created, a source with a frequency of 2.7 using the same data that was already in problem 2b. All right, so let's do that. So this all is going to look the same at the beginning. Okay, so we have 0, 10, 11, and we want to generate at x with a period equal to 1 divided by 0.7. And then we want the signal to be generated from 0 to 10 with a whole bunch of points. And we want y signal at x signal with a period equal to 1 divided by 0.7. Okay. And then we're going to create new data also at x. But in this case, we want the period at a frequency of 2.7. Okay, so we're going to an even higher frequency than the Nyquist frequency, or higher than our initial frequency, excuse me. And then we're going to also generate the underlying signal, also with a period of 1 divided by 2.7. And the plotting is all there, so that looks good. Okay. And what we see here, all right, so what we see here is that while we're looking at a very different frequency, this higher frequency, the orange curve, which is oscillating more rapidly than the blue curve, all of the observations occur at exactly the same position. Okay? So this is what is meant by the Nyquist frequency. We're essentially trying to search for frequencies that are too high, given the fact that we're making one observation every unit of x. And so we can alias any frequency higher than this Nyquist frequency with integers of the frequency that we're looking at. Okay. So here is what you need to remember about the Nyquist frequency, right? If you're going to obtain observations at regular intervals, and that part's important, right? So every 30 seconds, every 24 hours, whatever your measurement interval is, there's a specific signal, and there's a specific signal that you wish to detect, then be sure to sample the data so that the Nyquist frequency is greater than the frequency that you are hoping to detect. Okay? For every frequency that is greater than the Nyquist frequency, f will be aliased with f plus or minus 2n times the Nyquist frequency, where n is an integer. Okay? And in the previous example, the Nyquist frequency was 1, which is why we did f plus 2, so 0.7 plus 2. Right? So practically speaking, this means it doesn't even make sense to bother searching for any signals with f greater than the Nyquist frequency. Okay? But there's one more thing, one more saving grace. Okay? In the literature, it is often stated that there is no, let me reset that sentence. There is no Nyquist limit, though, if you have unevenly sampled data. So if you're using ground-based data where there are gaps, or where you don't return exactly every 24 hours later, there is no Nyquist limit. So you don't have to worry about an inability to find very short frequencies. Okay? So for any ground-based observing, you can search for extremely, extremely short frequencies. Right? And we'll talk about caveats to this a little bit later in the notebook. Okay. Now, staying on the topic of non-continuous observations, without derivation, I'm just going to present to you the discrete Fourier transform. Right, so we have the discrete Fourier transform is equal to the sum from n equals 0 to capital N of g sub n e to the negative 2 pi I f n delta t, where g sub n is equal to g, the continuous function we had previously, sampled at intervals of delta t. So n is some integer. You're just coming back every delta t to get a new sample of that continuous signal. Okay. The discussion that we just had tells us that the Nyquist frequency won't allow us to detect frequencies that are greater than 1 over 2 multiplied by delta t. So the relevant frequencies to search for power given delta t are between 0, essentially extremely long periods, okay, and the Nyquist frequency. And we can sample those relevant frequencies on a grid from delta f is equal to 1 over capital N delta t. Okay. All right. So from there, we basically get that the g hat sub k is equal to the sum from 0 to n of g sub n e to the negative 2 pi I f k lowercase n capital N, okay? Where g sub k is equal to g observed at the specific frequency k multiplied by delta f. Okay? So this equation, this is the discrete Fourier transform. Okay? Now, from the discrete Fourier transform, we can calculate the periodogram, which is an estimator of the power spectrum. Okay? So everything we'll be working with today is an estimator of the power spectrum. It's not the power spectrum itself, but it's a measurement of what we expect the power spectrum to be given the data at hand. Right? So the power spectrum of f is equal to 1 over n, the sum from n equals 1 to n of g sub n e to the negative 2 pi I f k n capital N squared. This is called the classical periodogram or the Schuster periodogram. And again, this estimator allows us to take some continuous signal that has been sampled at regular intervals and determine what are the frequencies that are most dominant within that signal. And so that, all right, is our brief reminder of Fourier analysis. And now we're going to talk about the Lomb-Scargle periodogram. Ultimately, what we care about as astronomers are applications where the data are not, in fact, uniformly sampled. And while I kind of hinted that Kepler took observations every 30 minutes, if you actually look at the full Kepler light curves, for reasons like adjusting the instrument, rolling the telescope, even Kepler data is not uniformly sampled. Okay? So knowing about the Lomb-Scargle periodogram is useful for all of us, no matter what sort of time series data we're looking at. Okay. The classical periodogram can be rewritten as the following. The PSD, or the power spectrum of f, is equal to 1 over n, sum from n equals 1 to n, g sub n, e to the negative 2 pi I f t sub n squared, where t sub n in this case corresponds to the actual observation times. Right? This is the same as just multiplying by the delta t's. Okay. Sorry, this is different because now the t sub n's are the actual time of observation. Excuse me, it's not regular intervals. Okay, so irregular sampling removes a lot of the nice statistical properties of the discrete Fourier transform. But Jeff Scargle was able to address these issues by figuring out a generalized form of the periodogram. Okay, and I am going to, though, today just use the fact that Scargle's modified periodogram is actually identical to the result that one obtains by fitting a sinusoid model to the data at every frequency f and constructing a periodogram from the corresponding chi-squared values at each frequency f. Okay, so we have some gnarly, very difficult, complicated sum here, which will get us an estimator of the power spectrum. But we also have this relatively straightforward method. You essentially fit a sinusoidal model to the data at the frequency f that you care about and measure the chi-squared for that model. Okay? You then compare that to the chi-squared you get for a constant model, and that is identical to this estimate of the power spectrum as well, to this periodogram. Okay? So the fact that these two things are identical is remarkable, and it actually is going to make our problem today much more straightforward. All right, so the model is just that y of t, given some frequency f, is equal to a sub f multiplied by sine 2 pi f t minus phase of f. Right? We can then calculate the chi-squared for every frequency f. Right? So the chi-squared is now equal to the sum on n of y sub n, the observation, minus the model value at the position of t sub n squared. Okay? The best model for any given frequency f requires the selection of a sub f and phi sub f that minimizes chi-squared. So we'll call this optimized model chi-squared hat. Scargle showed that the Lomb-Scargle periodogram can actually just be written as 1/2 of chi-squared hat minus chi-squared as a frequency of f, chi-squared hat as a frequency of f. where chi-squared naught is the value of a non-varying reference model. So I said this a moment ago, but again, we can estimate the periodogram, we can measure the periodogram, estimate an estimator for the power spectrum just by measuring chi-squared at every frequency that we might want to test f. This is amazing and wonderful. This realization that we could write things this way by Scargle allowed further generalization of the Lomb-Scargle periodogram because we can adjust our chi-squared value to include the measured uncertainties. This is not possible in, say, the discrete Fourier transform. There is no natural way to include the uncertainties on the individual measurements. And this is wildly useful because we know that the uncertainties on individual astronomical measurements vary, right? So now we have a chi-squared, which is a same sum we had before of the observed y values minus the model values, normalized by the individual uncertainties squared. Okay, great. So now we have what we need to know in order to construct a Lomb-Scargle periodogram. We'll spend the last bit of the lecture actually building the Lomb-Scargle periodogram. All right, so for problem 3a, I would like for you to write a function called chi2 to calculate the chi-squared given f, a sub f, and phi for observations y sub n, each with uncertainty sigma sub y sub n. And we're going to have some sampling interval t sub n. Okay? Now, for a future problem, you'll find that if you store a sub f and phi in a single variable called theta, where a is equal to theta 0 and phi is equal to theta 1, that's going to make our lives easier later. Okay, so let's do that. All right, so we need to write this chi2 function. All right, so we have a and phi coming from theta here. And now what we need to do is calculate chi-squared. So we said that it is equal to the sum of y minus the model. Okay, so y minus the model. The model in this case is a multiplied by the sine of 2 times pi x divided by f minus our phase phi. Okay, so y minus that's squared, and then we want to divide that by the uncertainties squared. Okay, so we have now our chi-squared, and we ultimately want to return chi-squared. Okay, let's execute that. No errors so far. Okay, so now we want to write a function to minimize the chi-squared given everything but a sub f and phi sub f. And the easiest way to do this is using the minimize function in SciPy. If you haven't seen that before, basically what you do is you can pass in some function that you want to minimize, the parameters that are allowed to vary, and then any arguments, essentially data upon which the model is going to be conditioned. Okay, you can provide those three things, and then SciPy will figure out the optimal values for your variables. Okay? All right, so in our case, we want to complete this line here. And we have a little typo. That should be parentheses instead of brackets. But we're going to pass in the function that we just created, chi-squared. We're going to pass in the variable that can be varied. That's theta. And then we need to pass in the arguments, basically the data, which are going to be used to condition the model. Okay, then we can execute that. No problems there. Excellent. All right, so next we want to write a function, LS periodogram, to calculate the Lomb-Scargle periodogram for the observations y sigma sub yt over a frequency grid f grid. So we're going to basically provide many different frequencies to then try to measure the power in order to create the periodogram or estimator for the power spectrum. So here we're inputting all the data plus f grid. We then have the PSD, the power spectral density, equal to an empty array of the same shape and size as f grid. We need to measure chi-squared hat naught. That's just y minus the mean value of y, and then the sum of all of those normalized by the uncertainties squared. And then for every frequency, we want to measure what is the chi-squared for that frequency after we minimize the chi-squared by varying the amplitude and phase, and then put that into our array for the power spectral density. Okay, no problems there, nothing we had to fill in. Okay, so now we want to generate a periodic signal with 100 observations taken at random intervals over a time period of 10 days. We'll use an input period of 5.25, an amplitude of 7.4, and a variance of the noise of 0.8. We then want to compute and plot the periodogram for all of this simulated data. When doing so, do you find that you can recover the simulated period? Let's figure this out. All right. Here's a hint for this problem. We want to set the minimum frequency in the grid to 1 over t, where t is the duration of the observations. Essentially, what is the time between the last observation and the first? And then we want the maximum frequency to be 10 in a grid that has 50 points in it. Okay. So we'll see that most of the code is here. We're generating the data along with some uncertainties, and then we need to figure out what is the size of the grid. Okay, and well, that's the answer, but it shouldn't be there. So let's delete it real quick, and then we'll add it right back in. Okay, so we want 1 over capital T, which is the duration of the observations. That is essentially the maximum value of x minus the min. NumPy has a nice function for that called PTP, or peak to peak. And so we can just say 1 divided by peak to peak of x. We want a maximum frequency of 10, and we know we want 50 spaces in our grid. And then we can calculate the periodogram. So let's run that. Ooh, that was fast. You all write really good code. You write really good code. Okay, now we want to plot the results, and there's nothing for us to add here, so let's just execute this cell. Okay, and what we have in this case is an estimate of the power spectrum, and basically the peak of the power spectrum corresponds to the frequencies that are most dominant within our signal. And in this case, we can see that the peak, right, the most power occurs at a value of about 0.5. That's actually very different from the correct period of 5.2. Okay, so what's going on? Let's think about this. Okay, let's use the same data, but this time instead include 1,000 points in F-grid instead of 50, and then calculate and plot the periodogram. Okay, let's do that. Let's see if anything changes. So in this case, we have a new F-grid. We want 1 divided by peak to peak of x up to a value of 10 with 1,000 data points. Okay, let's execute that. All right. Ooh, all right, this is a little bit slower. That makes sense, though. We have to evaluate 1,000 different calls to this optimization code to measure the chi-squared instead of just 50. It makes sense it takes a little bit longer. It was done even before I was done talking. Okay, so we have some new best fit period. Let's execute this. Okay, and we see, oh, that looks really nice, doesn't it? Okay, we now have a strong peak, one that's much stronger than any other peaks here in the data. And that peak occurs at about 5.25, exactly the period that we expect. So now, just to confirm that everything is looking good, let's plot the phase folded data at the newly found best fit period. Okay, so we want to create a phase plot. We have data x and y. We have a best fit period, which is within F-grid, and we just want to use NumPy argmax. We basically want the maximum value of the PSD. Okay, that's how we get the period. And then we also have some uncertainties on the data. So let's execute that. LSPSD is not defined. Oh, that's because we called it PSDLS. That would make sense, wouldn't it, everybody? Okay, let's swap that out real quick. PSD of LS. Let's execute that. Ooh, and that's looking pretty good, isn't it? That looks like a periodic signal. That looks like we recovered the correct period in this data. So, congratulations. You did it! Just now, in those few lines of code that we just wrote, you developed the software that is necessary to find periodic signals in sparsely sampled noisy data. Basically, all of the challenges that I have been highlighting throughout the week about why it is difficult to work with time series data in astronomy, we just overcame all of them we had some gappy, weird light curve, and still we were able to pull out the correct period. Okay? So with that, I bid you adieu and say you are ready to conquer LSST. Are you, though? Are you ready to conquer LSST? There should be a couple things about what we just did that maybe are causing you to wonder or worry a little bit before you run out and take over all of the Rubin Observatory. Right? Like, for instance, why did we first use a grid that only had 50 points in it when trying to estimate the frequency, and then we used a grid that only had 1,000 points in it? What's with that? Because it seems like 1,000 points worked, but 50 clearly didn't. Okay. So there's actually several important ramifications following the choice of the grid you use when building a Lomb-Scargle periodogram. And this will be true for other techniques that we cover this week as well. Okay. When you select the grid upon which to evaluate f, you have to both determine the limits of that grid. So what's the minimum frequency to search? What's the maximum frequency to search? But you also have to figure out what is the spacing of the grid, right? How many evaluations do you make within whatever your frequency limits are? Now, fortunately, the minimum frequency, right, or think about this as the longest period that you can detect in the data, that's really straightforward. That is basically just 1 over capital T, like we did in the problem. We didn't say this at the time, but this corresponds to a signal that goes through one periodic cycle over the full span of your data, right? So if you have some periodic signal and you only sample 10% of a single phase, you'll never actually be able to constrain the period. So you know you have to go all the way out to a frequency corresponding to one full cycle within the data. Now, computationally, if you want to just set this minimum frequency to 0, that's not going to change how much time you really have to spend on the problem. Okay. A little more tricky is the maximum frequency. Now, we discussed in detail earlier that the maximum frequency is typically the Nyquist frequency, because you won't detect signals at frequencies that are greater than the Nyquist frequency. Okay. But the caveat with that is that the Nyquist frequency only applies if you have evenly spaced data. What if, as is the case for us, you have unevenly spaced data? And then there is no such thing as the Nyquist frequency. There's a lot of ad hoc methods in the literature. One that comes up a lot is to just create a maximum frequency that is equal to 1 over the mean value of delta t, where delta t is the mean separation between consecutive observations in your time series. Okay? This is not correct, and this is not a Nyquist frequency or a strict limit to the maximum frequency that you can detect in your data. Instead, my practical advice, and I think this is a case where practical advice trumps very detailed mathematics or anything like that, is to just set the maximum frequency to the highest frequency that you might expect to see in your data. Okay? So for example, with the exception of only the very smallest white dwarf systems, there are no stars that show periodicity at timescales of less than an hour. Okay? So most of our frequency searches could be limited by 1 hour. That's the highest frequency for which we might expect to recover any signal. Okay. Now, we have a min, we have a max, but we still don't have a grid because we haven't decided what is our spacing delta f going to be. And we saw from the previous examples, if you have too few points, like 50, then you won't resolve the peak in the periodogram. Okay? Alternatively, if you have far too many points, you're going to end up doing a lot of computation that otherwise isn't necessary, right? You could always do 10 million points in your grid, but if you have to do 10 million evaluations of the chi-squared and you have to optimize 10 million different chi-squared minimizations, that's going to take a long time, especially considering there are billions of sources that are going to be detected by the Rubin Observatory, right? Fortunately, you can determine a pretty good estimate of delta f, and this goes back to the Fourier pairs that we discussed earlier in the lecture. Okay. The window, that basically the duration of your observations is equivalent to a top hat. So that means that all of the delta functions that are showing up in your power spectrum are going to be broadened by a sinc function with a width related to the duration of your observations, or 1 over the duration of your observations. Okay? So we want delta f, basically all of the frequencies that we sample, to sample 1 over tau. So that means that delta f should be equal to 1 over n naught of t. So I said tau a second ago, I meant t. Again, t is the full duration of your observing window. Okay? In this case, 5 is a pretty good number to use for n naught. So now we have a minimum, a maximum, and how regularly we sample in between those two. Okay, so now for our final problem, let's figure out what the optimal frequency grid is going to look like for Rubin light curves. All right, so we're going to assume that time is measured in days, the survey runs for 10 years, and that the observations cannot recover periods less than 1 hour. So ultimately then, what is the size of our frequency grid? Okay, so our minimum frequency is just 1 over the time, the duration of the observations. So that's going to be 1 over 10 times 365. Our maximum frequency, as we said, 1 hour. So in days, 1 hour is 1 divided by 24. Okay. And then we want delta min to just be f min, okay, or 1 over capital T divided by 5. So now we can figure out what our grid should be for Rubin Observatory and how many points are going to be in that grid. All right. All right, we're going to need to do, for typical Rubin light curves, something like 400,000, maybe even 450,000 different samples within our frequency grid. All right, we're now talking about a couple of order of magnitude more than the 1,000 that we did for the example problem. And that grid of 1,000 took us a few seconds. So if we're going hundreds of seconds for every single source, and we have at least a couple tens of millions of sources, but if we want to run everything, we're talking about tens of billions of sources times 100 seconds. That's literally trillions of seconds. And yes, we can do things like parallelize that calculation so that it goes a little bit faster, but that is a lot of time. Okay. Fortunately, very, very, very fortunately, there are faster implementations of the Lomb-Scargle Periodogram than the pure Python method that we developed as part of this notebook. And so in the notebook number 3, the problems that we're going to do there, we're going to reinforce some of what we learned in the lecture, while also implementing a much faster version of Lomb-Scargle, which has been developed as part of AstroPy. So that's the end of the lecture, and I hope you look forward to the notebook on the Lomb-Scargle Periodogram. Thank you.